Here's a quick recap of the previous lesson. We considered the multiplicative group U13 and its subgroup H containing the elements 1, 3, 9. And then we formed the set of distinct cosets of H, which we called U13 mod H. And that set contained four distinct cosets, namely 1H, 2H, 4H, and 7H. Then we formed a group using this set of cosets of H. And we're going to introduce a new terminology here. Such a group whose elements are cosets is called a quotient group. And the operation of a quotient group is coset multiplication, or coset addition if your original group happens to be an additive group. Now let's review how coset multiplication works. So suppose we want to multiply 2H by 7H. And so we have 2H, after all, is a coset, so here are the elements of 2H, and then here are the elements of 7H. And in order to multiply those two cosets, we just multiply every element of 2H by those of 7H. So 2 times 7, 2 times 8, 2 times 11, 5, 7, 5, 8, 5, 11, 6, 7, 6, 8, 6, 11. All of these modulo 13. So let's do the computation once again. So 2 times 7 is 14, mod 13 is 1. 2 times 8 is 16, mod 13 is 3. And then 2 times 11 is 22, mod 13 is 9. Okay, let's go to the next set of three products. So 5 times 7 is 35, mod 13 is 9. 5 times 8 is 40, mod 13 is 1. And then 5 times 11 is 55, mod 13 is 3. So we didn't get any new elements. This is consistent with what we saw in the previous lesson. And then three more products here. So 6 times 7, 42, mod 13 is 3. 6 times 8, 48, mod 13 is 9. And then we can probably guess what that last product is going to be, but let's actually do it out. 66 mod 13 is 1. And so, really, there are only three elements in this product, and 139, in fact, is our original subgroup. And so 2H times 7H would be H, or 1H, that we see right here in U13 mod H. So 2H times 7H happens to be equal to 1H. And that's how we do coset multiplication. And here's the group table for U13 mod H. For instance, we just computed 2H times 7H and found that the product was 1H. So as a review, let's go through the group properties to actually verify that U13 mod H is a group. So we'll start with closure. Well, we can see that all of the products are in fact the four cosets in U13 mod H, and so it is closed under coset multiplication. Associativity, as I mentioned at the last lesson, please check out Chapter 21 reading to see why coset multiplication is in fact associative. The identity element is 1H, and we can see that by looking at the first row of the table and the first column of the table. In other words, multiplication by 1H doesn't change anything. And last but not least, inverses. And so in the calculation that we just did, we saw that 2H and 7H multiply together to be 1H. And in fact, if we do 7H times 2H, we also get 1H. And so 2H and 7H form an inverse pair, and we can say that 7h is equal to the multiplicative inverse of 2h, or we can say that 2h is equal to the multiplicative inverse of 7h. And we also see that 1h and 4h are self-inverses. And so in fact, U13 mod h is a group under coset multiplication. Coset multiplication is rather tedious, but fortunately we found a shortcut for this process. So last time we saw that for a pair of cosets in U13 mod h, that AH times BH is equal to ABH. So we just multiply the coset representatives. For example, according to this shortcut, we should have that 2h times 7h is equal to 14h. 14 is 2 times 7. And we've seen, in fact, that 2h times 7h is equal to 1h. And notice that 14h is the same as 1h because these coset representatives, 14 and 1, are elements of U13. And so when we reduce 14 mod 13, we get 1. And so the calculation we did earlier in today's lesson is consistent with the coset multiplication shortcut. In our last lesson, we proved that if a group G is commutative, so for example, if G were equal to U13, then the coset multiplication shortcut holds in G mod H. But we've also seen that the shortcut holds in D4 mod Z, where Z is the center of D4 containing the identity element and R180, even though D4 is a non-commutative group. And so this picture doesn't tell the entire story about when the shortcut holds in G mod H. Now please pause the video and work on day 22 classwork, and afterwards we'll go over some of the problems and concepts. And one word of caution, please do not use the coset multiplication shortcut when working on problem number 2. Let's talk about problem 4, where we were asked to find the multiplicative inverse of 15h in U37 mod h. And recall here, h is a cyclic subgroup generated by 10, which contains the elements 1, 10, and 26. So, to find the inverse of 15h in U37 mod h, so we're looking at this coset, we first work in U37. In particular, we're working with the coset representative 15. And so in U37, we find that 15 times 5 is 75, mod 37 is 1, and therefore 15 and 5 are inverses of each other. In particular, the inverse of 15 is equal to 5. And now we use this to find the inverse of 15h and U37 mod h. So let's start with a calculation. If we multiply 15h by 5h, then we can use the shortcut to multiply the coset representatives, 15 times 5h. But we just saw that 15 times 5 is equal to 1, and so we end up with 1h. In other words, 15h and 5h are inverses of each other in U37 mod h because their product is the multiplicative identity. Now, how do we write that down symbolically? Well, we have the inverse of 15h is equal to 5h. But then just focusing on the coset representative 5, which is in U37, we found that 5 is equal to 15 inverse. And so we can rewrite this as 15 inverse h. And I'll highlight the substitution we made for the coset representative. And therefore, our conclusion is that the multiplicative inverse of 15h is equal to 15 inverse h. And it looks like on the surface that we're just moving around the -1 exponent here, but the reasoning is all in the calculations that we just did above. And in general, there's nothing special about 15. And in fact, the multiplicative inverse of AH is equal to A inverse H. Now let's verify that U37 mod H satisfies the group properties. And a couple of remarks here. First, we know that U37 mod H satisfies the Coset multiplication shortcut because U37 is a commutative group. And the second remark is that U37 mod H contains 12 cosets, and building a 12 by 12 table just seems too daunting. So rather than building that table, let's use the shortcut to make many of our arguments. Let's start with closure. So given a pair of cosets, AH and BH in U37 mod H, in particular, we know that these representatives A and B are in U37. So when we multiply these cosets by the shortcut, we get ABH. But because A and B are in U37, and we know that U37 is closed under multiplication, then AB must be in U37 as well, and therefore ABH is a coset in U37 mod H. And thus we have closure under coset multiplication. Now, as mentioned earlier in class, coset multiplication is always associative. Please take a look at chapter 21 reading for that. For the identity element, we claim that the coset 1h plays the role of the identity, and let's verify that using the shortcut. So for any coset AH, 1h times AH, well, we just multiply the coset representatives and get 1 times AH, but 1 times A is just A, and so the product is AH. In other words, 1h times AH is equal to AH, and then we also have the other way around. I'll leave the argument to you that AH times 1h is equal to AH, and therefore 1h is the identity element of U37 mod H. And last but not least, inverses. So given a coset AH in U37 mod H, we consider the coset A inverse H. Now, how do we know that such a coset exists in U37 mod H? Well, because, again, the representative A is an element of U37. And U37 being a multiplicative group, A inverse must exist in U37, and therefore this coset does exist in U37 mod H. And then when we multiply AH times A inverse H, we once again just multiply the coset representatives. They cancel in U37, and therefore we have the product 1H. And I'll leave it up to you to verify similarly that A inverse H times AH is equal to 1H. And thus, A inverse H is the multiplicative inverse of AH in U37 mod H. And that concludes our verification that U37 mod H is in fact a group. And we call it a quotient group because its elements are cosets. Now, all of the arguments in this verification that U37 mod H is a group really depends on the fact that U37 mod H satisfies the Coset multiplication shortcut. In other words, what we just proved is the following. If the Coset multiplication shortcut holds in G mod H, then G mod H is a quotient group. Once again, if the shortcut holds in G mod H, then G mod H is a quotient group. But the question remains, when does the shortcut hold? We know a partial answer, when G is commutative, for instance. But we've seen that there's more to the story than that. So in the not too distant future, we will resolve this question. But for now, please stay tuned. And that's the end of today's lesson. And I will see you next time.